And almost finally, number 10. Let H be a subgroup of G so that conjugating any element H by any element G keeps you in H. Right? So G inverse HG is still in H for any G and for any H. So we have a subgroup H with that property. It's closed under conjugation, you could say. Prove then that it also has the property that GH equals HG, that left cosets and right cosets are equal for any G. That's true. A subgroup which is like this is called a normal subgroup. These are two equivalent properties of normal subgroups, that left and right cosets are the same, and that they're also closed under conjugation. And normal subgroups are great for a lot of reasons. So here's one quick way to get from the first thing to the second thing. So G inverse HG is in H, right? That's what we know for any element H. Now, so what do you think this would be, right? So if here we have well, yeah, actually that's a great idea. So here's a left coset GH. We want to prove that this is equal to HG, right? This is true for all G in G, for all H in H. So GH, we want to prove that that's equal to HG. Okay, well, here's the idea. Let's replace H with G inverse HG. Now, why is that legitimate? Because if this is always in H, well then surely if you do it to the entire set, you would get the entire set back. Because multiplication on the left and on the right in a group are both bijections, so surely doing both of those things to H, two elements of H, will get you the full group. So then you go from here, and so you get G inverse HG, and of course G and G inverse cancel each other out, so you get HG. So boom. So a couple students found this path. I thought this path was brilliant. It's the shortest one available, I believe. But there's also other perfectly good paths, which I'll talk about. You can go. You can do the both of them are subgroups of subsets of the other route. You say if something, say, pick a GH in GH, and give it one of these clever maneuvers. You say, you give it like a. I saw a lot of people do this. You give it a G inverse G like that. Well, I won't even write that now. And then you look at it like this: G inverse H, G inverse G. And then you say, well, look, aha, that meets this definition. It's the inverse of something in, it's the inverse of something in G times H times that thing in G. It's just in this case that's G inverse, which is kind of wacky, but that's totally legit, totally legit. And so that's so what should you say? I guess maybe you should say something like this is equal to H2 or something. That's kind of, I don't know, maybe that's a stupid way to do it, but like this part is equal to H2 in G, so you can just say it's in HG or something like that. Or you can just go straight from there. Maybe you just reference that thing and say, so there you go, that's in HG like that, or whatever. So there you go. That's one way, and then the other way is much easier, frankly. You start with you don't have to do that weird inverse thing. You start with HG like this, and then you say, well, look, it's maybe I should be more clear. So this part means that GH is a subgroup of HG. So then the next part you say, well, start with something from HG, and you see that that is the same. We can give this a G inverse HG. And then those three things on the right, we know that that's equal to something in H. And so you could give that a name, or by the same token from last time, you can just say that that's in GH like that. So there you go. So then that part proves that, oh, 1 second. Having technical difficulties here. That HG is a subset of GH. And so then since you have it both ways, then you've proved it. That they're equal. But of course you also proved that this way too. You went from here and you said equals HG. So great. So that way is fine too. So whichever way you did it, great job. Most people got that one. Okay. We will stop there.